Thanks for coming to Seajure. I'm going to be presenting a talk that I gave at the Clojure Conj about 2 or 3 weeks ago as an unsession, which is titled Experiments with Grail, or as I've been convinced to call it recently, Graal is the officially supported pronunciation of the term, although it is Old English or French for Grail, so I think there's a reasonable interpretation of Grail as the name. But let's start with talking about what Graal is, and there's two major aspects of it. The project itself is built on the concept of a substrate VM, and running Clojure, we're familiar with the concept of a virtual machine because all Clojure code gets compiled down to JVM bytecode and run on the Java virtual machine. The goal of Graal is to provide a lower level substrate VM that is applicable to more than just the Java runtime, but can actually have multiple other languages mapped to it. So one axis of the Graal project is to provide support for a polyglot language experience where you can write Clojure, you can write Java, you can write Ruby and Python and all these other languages, even stuff like C and C++, or things that compile with LLVM that will ultimately be able to be written as substrate VM or SVM bytecode and run by this universal compiler or universal runtime. And that gives you the ability to write code in different languages that then communicates with each other. And we've got a couple of possibilities for doing this right now with stuff like J and I in Java, so you can call out to C code from your Java or Clojure code. But rather than having this foreign interface to other languages, this provides a more native way to interop between these different languages. This talk is not going to cover any of that. Mostly, so far, I have been focused on the second axis here, which is that the substrate VM also provides a way of building standalone binaries. And my main motivation here was wanting to build programs and tools in Clojure and be able to use them interactively. And Clojure has a great command line argument library, tools.cli. You can definitely write command line tools in it. That's almost always the first thing I write in a language is a simple tool to kind of kick the tires. But the problem with Clojure as a CLI platform is it's really slow to start. Java and the JVM have had many engineering hours put into them to make them fast once it's running, and the JVM can be a very high performance runtime for long running programs, but there's this initial startup cost that is pretty painful, especially when you have something that you want to run many times by hand interactively from a terminal. And there's a few reasons for that. One, booting up the JVM by itself is on the order of 100 to 500 milliseconds. Loading Java classes takes the bulk of the time, and in particular Clojure core, due to the way Clojure is compiled, you wind up using a ton of different JVM classes, and as a result that means you can pay up to several seconds of initialization time as a cost, even if all you want to do is echo something to standard output and then exit right away. So again, doable, but not a great experience for a command line tool. And one of the second big things that Graal lets you do is build native images that embed the substrate VM along with your compiled code so that you can get the speed and resource usage of a native executable, even though your original language was something extremely high level like Clojure. Also, feel free to stop me with questions if you guys have anything you're curious about. So, to motivate this talk and scratch a personal itch, how many people have used JQ, the command line tool? Okay, so about half the people here. For those who haven't, JQ is really useful for interacting with JSON code. And at its most basic, it accepts information on standard in, formatted as JSON. So we can give it a simple object here, and it will pre-print it for us. Pretty useful, especially if you are dealing with a big block of JSON from an API. So for example, if we call this like mock JSON endpoint, this is already pre-printed for us, but in many cases it wouldn't be. And we would have to interpret this by hand or get a big block of JSON text. So the most basic thing we can do is feed that into JQ, and this is already better, right? We've got colorized output. Human eyes are really good at picking up on visual information like color, so we get a much better sense of what are the keys versus the values, what are numbers versus strings. JQ can also do other things instead of just pretty print, so we can, for example, map over all of these and pull out the user ID. Say we wanted to find out how many times each user had made a post. Well, this is a fake API, so they all have exactly 10, but this lets you use and compose JQ with other parts of the Linux toolset, which is really cool. But again, we use Clojure, so most of the time we're not dealing with JSON. Most of the time we're working with Eden. And I've got a example file here, which is actually drawn from one of our APIs here at Amperity, which describes how authorization works in the platform and which people are allowed to do which things. That's a lot of Eden, and as you can see, it is not pretty printed for us. So for a long time, I've wanted the equivalent of JQ or EQ. There is actually an EQ, except it is written in OCaml, and there are no binaries distributed, so you have to compile it yourself. No one I know has successfully compiled this themselves. So this was a bit of a non-starter. And again, as a motivation for this talk, I wrote something very simple called Eden Tool. This, for those following along at home, does have a published release with some binaries if you want to play around with this later. But I'll walk through the code first because it is almost painfully simple. And I haven't implemented a lot of the filtering and mapping features from JQ, but at its most basic utility, it takes Eden on standard in and it pretty prints it to standard out using another library of mine called Puget. And the code, again, dead simple. It's like a REPL except without the eval. So we're reading, we're printing, and we're looping again until we're out of input. And here's the main function. That's it. 72 lines of code, including whitespace. And all we do is set up the printer, read from the input, and write to the output. So what does this look like in practice? Well, before we get to this mess of data, I'll just run this directly so we can see what it looks like. And it's probably booted up by now and is waiting on standard in. So I can do something similar here. Puget is a canonical printer by default, so it's reordered the keys a little bit so they're in alphabetical order. But again, basically it's just colorizing and pretty printing this. And you can set some options. So if I say width 10 here, it should line wrap for us. So you've got a couple of formatting options you can feed into it. But the main goal is just to pretty print stuff and make it a little easier to read. So what happens if we feed in that giant block of Eden from before? There we go. So it ran. It pretty printed the whole big block for us. This is definitely easier to understand than the single line of no whitespace Eden that we had before. But I'm sure you noticed there was a bit of a pause there before this thing kicked in. And to be fair, line run is actually starting up 2 JVMs and loading 2 entire sets of classes into it. So this is far from the fastest thing. But to make this more real, I'm going to use time, which is there's a time built into the shell, but we're going to use user bin time because it gives a more standardized output. And in addition to the elapsed time, this L flag will have it measure the resources that this process is using. So let's do this again. Cool. So real elapsed time, about 5.5 seconds from the time we invoked this to the time that it finished running. The process as a whole used a little under 250 megabytes of RAM, which is not very lightweight for something that you're running on the command line. This is okay for like a microservice or some long-running process that's doing a lot of data processing, but is not something you really want to run in the background or to have reserved each time you run this tool. And the other thing I want to point out here is context switches. And a context switch is effectively any time your program has to give up control of the CPU to something else for it to execute. And typically, the more context switches you see, the more times your program had to pause, the longer it's going to take to run, and the worse performance you're going to get out of it. So about 27,500 involuntary or forced context switches, in addition to the 248 megs of RAM or so. But wait, I can hear you say, can't we avoid a bunch of this compilation by doing an ahead-of-time uberjar? Well, yes. So if you look down here, I've got an uberjar profile that specifies the name and has this AOT all directive. And what this is going to do is, normally when you have the Clojure runtime load in a source file, it's going to actually read in the straight Clojure forms, do the compilation to produce the bytecode, and then have a representation of that loaded in the class loader in the process. But you can also compile things ahead of time, which means what we're going to store in the resulting jar is not raw Clojure source. It's also going to have the actual compiled Java class files in there. And usually, if you're distributing a library, you don't want to do this because you want to let people compile it with whatever version of Clojure they're using. But in this case, if we're building a self-contained tool, we do want to do this because we know no one is going to come along and need to recompile these files. So I'll just do that now. And this should be pretty quick because, again, tiny program, almost no dependencies. 10 seconds, not bad. So let's compare and see what the difference is. Again, 5.5 seconds, 248 megs of memory, 27,500 context switches. But this time we're going to use Java directly. Oh, that was much faster. Only 1.7 seconds, 162 megs of RAM, so significantly fewer. Again, running half as many JVMs, so that's to be expected. And only 7,800 context switches, which is part of it being faster in general and running more efficiently. We didn't have to do any Clojure compilation. We got to jump right into the Java class files. We still had to load those into memory, but this is a lot closer to being a tool that we could use from the command line. Great. However, we can do better. And that's where Graal comes into play. So to exercise that, I have set up this pretty simple makefile here. I'll skip the part at the top for the salient bits at the bottom, which is basically that we need to compile an uberjar. We need to call the native image tool in Graal, which is what's going to take the precompiled JVM code and turn it into a native image by embedding the substrate VM. And then we need to give it, for Clojure specifically, we are sort of forced to use this flag to the native image compiler called report unsupported elements at runtime. Because of the goal to provide a universal substrate, the set of things you can do in a Graal native image is not the full set of things that you can do inside a JVM. In particular, one that hits Clojure pretty hard is you cannot compile new bytecode. That basically removes all uses of eval. It impacts a lot of reflective calls and generally limits the set of ways that your program can behave, because in order to fully trace your program's behavior and build a native image out of it, Graal needs to know that certain things are not going to be possible ahead of time. Otherwise, it will blow up at compile time. What this flag does is instead of blowing up at compile time, it inserts bytecode in those locations that throws a runtime exception. And if you know your code is never going to call those code paths, then that's fine, because you'll never get that exception at runtime. But you still want to be able to compile the image in the first place. So this is not ideal, but it makes it possible, so we're kind of stuck with it. And I'll talk about some more advanced uses of the Substrate VM in a little bit that let us work around some of the restrictions on behavior that you run into if you start trying to write more sophisticated programs and turn them into native images. But for this extremely simple example, this is basically all we need. But first, I need to tell it where Graal is. Okay. So, what is Graal doing when it makes this native image? Well, I already talked a little bit about how it traces your program behavior. Another thing that it does is it does tree shaking, so it figures out what parts of the JVM you actually need and what classes you wind up loading, because it will actually fully load your program's state at initialization time and freeze a snapshot of the heap and embed it in the native image. This has the downside of making the native image a little bulky. Like, it's definitely a bigger binary than you're probably used to for a natively compiled tool. But that's one of the things that lets it start so fast, is that it is literally loading up the initial heap and jumping right into it at execution time. This introduces a number of additional restrictions, or is the driving force behind them existing in Graal. So among them, you must have resolved all of the classes you're going to need at compile time, not at runtime, and that gets back to the no reflection restriction. You can't have any running threads in your program at compile time, which is a terrible idea in general, but you can't do at all with Graal. And there's one more I'm forgetting about, the initial state needing to, there's a flag that lets you defer some class initialization until runtime instead of compile time for exactly this reason. If you are working with a third-party library that you don't have control over, there are some ways to prevent things from happening at compile time and defer them until runtime, so you can avoid side effects like that. And this will be a theme that you'll see repeatedly with Graal, which is ideally things would happen one way, but in many cases you don't have control over that code. So rather than make you fork the library, patch it, and build it yourself, Graal gives you these escape hatches to work with, so that you can get stuff to compile while those upstream libraries work on their compatibility. So not bad, about 2 minutes to compile a native image of this relatively simple binary, including the time it took us to build the Clojure uberjar. As you can imagine, tracing through all this execution and figuring out how to turn that into native code is not a simple task. So this gets a little bit slower, but mostly takes more memory for more complex programs from what I've seen so far. But now, let's just kick the tires on this thing. Seems to be working. We've built a native binary at the project root. It's about 28 megabytes uncompressed, so again, probably bigger than you would expect to see a native executable take up space-wise, but it's pretty fast. Let's motivate that with a real example. So going from line run to an uberjar got us down to 1.7 seconds and 162 megs of memory. If we use the native image, that took 17 milliseconds, or sorry, 170 milliseconds, and only 83 megabytes of memory. So our resource usage is down substantially. The responsiveness is effectively real-time as far as the human is concerned. And you can see that reflected down here. We only had 220 context switches. So this thing basically ran almost full-time on the CPU compared to the two prior versions. And that was a pretty big input set of data. So most of the time spent was probably just writing all of this to standard out. Questions so far? Cool. So that is sort of the very high level version of how you can use the native image tool with Graal to speed up your Clojure programs. But now I wanted to move on to a more complicated example that is slightly less of a toy problem and addresses a need that we actually have here at Imperity, which is running a monitoring daemon on our hosts. Who here is familiar with or has used Riemann before? Cool, we have some people outside Imperity. That's good. I'm not going to go into too much detail about Riemann because this is a extensive topic. There's a lot of depth here. I would strongly recommend watching the talk here if you're interested. But at a high level, Riemann is a monitoring system that is configured using Clojure code and a Clojure DSL, and generally operates on very Clojure-y principles about how it handles events and what they look like. And under the hood, all of the monitoring events are just maps that have some keys in them. So Riemann ships with a set of tools, which are command line programs that you can run on a host. And each of these command line tools measures a particular kind of thing. And there's like a high-level one for Riemann Health, which measures CPU, disk, and memory usage. And then there's a whole bunch of different ones you can run if you need to look at something more specific, which we use and have used across all of our hosts in Imperity's stack. But I wasn't fully satisfied with these as a solution for a few different reasons. One of them is that these are written in Ruby. And if anyone has tried deploying Ruby in production before, it's no picnic. It's a lot like Python, which is not a compliment. And having to coordinate the installs of a bunch of different tools depending on what you want to measure also means that you're paying the overhead of each of these processes per kind of thing you want to measure. And lastly, we just didn't have a lot of control over the metrics these things were producing. So there's a couple of reasons to want to do this a little better. So long ago, I wrote a tool called Solanum for replacing the Riemann tools and giving a YAML-driven DSL for configuring all of this in a single executable. So instead of running a different binary for your CPU, a different one for your uptime, a different one for your network, I figured we'll make this pluggable and put everything into one file and make it flexible enough to run one application that could do everything. Except I still wrote it in Ruby because that's what I knew, and that has all of the same problems of deployment and building something that you can just drop onto a host and have it work. So this seemed like another good example to use for Graal, because compiling this down to a native image, well, one, we get to write it in Clojure, but then compiling it to a native image solves the deployment problem because we can just drop a native image onto each host with no dependencies. It also solves the resource problem of writing it in Clojure because we really don't want to pay a 250 megabyte memory tax on every host just to run a JVM to measure stuff in the background. So I rewrote this. It's pretty quick. And then I set out to get it working with Graal, which I have saved us some time and went to do a compilation here. I actually have to make this smaller. Cool, so it built the Uberjar, and then we handed it off to Graal, except this time we got a whole bunch of warnings here. And these come from a couple different things, but generally this means that the code that we tried to compile is using some features of the JVM that are not compatible with the substrate VM. There's a few different ones here, but most of them come down to the fact that the Riemann Java client relies on Netty, which is an asynchronous I/O library, as well as Protobuf, which is a wire encoding transport mechanism. And both of them are trying to be high performance, which means they wind up using sun.misc.unsafe, which is a piece of the JVM that you are not supposed to use. Everyone uses it anyway if you need to do something high performance, because what it lets you do is reach into the in-memory representation of a data structure in Java. So if you know, you can ask it, like, at what memory location is this particular class's field offset from the start of this class, and then you can go dig in and pull that thing out directly instead of having to serialize or deserialize the whole thing. Great, high performance. We don't really need this for this particular use case, but it will break the native image we're trying to build. The only reason this compile succeeded is because I have the flag set to allow to throw those errors at runtime. But if we try and run this right now, it's going to blow up. Actually, maybe it won't. Let's find out. And then there's one other exception in here, which I'll get to in a second. But before we do that, so I have an example config file here, intentionally stripped down. It's just going to try and measure some basic properties about my laptop, CPU, uptime. Oops, that's not the right one. Demo config. There we go. CPU, uptime, load, memory, and checking that Postgres TCP port is open locally. And then for outputs, I've just specified print, which is just going to write all this to standard out. So let's try doing that. Oh, that actually did work. Because in this case, I'm not invoking the Riemann client, which is where all of that complexity and disallowed use cases are located. So that code path, like I said, if you know that the problematic code path isn't going to get exercised, then you can actually run the program just fine as long as you defer those exceptions. But if I were to change this and add and try and do this again. Oh, really? Oh, well, segmentation fault. There we go. So this is a particularly ungraceful way for this thing to blow up. And actually, this is the first time I've seen the seg fault here, so yay, testing in Linux gives you different bugs. But we collected and wrote all the events to the print output, which is still there, but then when we tried to report them to Riemann, it blew up, which makes this not a very good tool for monitoring things and sending events off of the host. So how do we fix this? Again, going back to that theme, Graal gives you mechanisms to work around these libraries that haven't been updated yet. And if we go and we look at these, the errors again, you can see that most of them are about the use of sun.misc.unsafe. And Graal actually does have some built-in pattern matching for code paths that use these unsafe attributes in a standard pattern. So there's a set of ways people do this that result in a predictable outcome. And the Graal compiler actually has automatic substitutions for those cases, which is why it's saying that it couldn't figure it out here. And fortunately, it provides us a way to go give it some more information and say, well, as humans, we can figure out what the intent of this substitution was, and then we can go tell Graal about it. So what that looks like, if you look at, so let's look at the Netty substitutions first. So you need to pull in a bunch of stuff from the substrate VM. So this requires a dependency on the Graal package. Oops, I'm still in Eden tool here. Which is available. Fortunately, they released it on Maven Central, so you can just depend on it the way you normally would some other project. And then that gives you access to these annotations. And we can declare a bunch of classes that look very unlike normal Java classes because we're not actually trying to compile working bytecode for these classes here. They're just really placeholders for us to give Graal some hints about what this code in this third-party library is trying to do. And so for each of the errors we ran into in that compile output, you can see that we are providing some hints about the field, the class name where it came up, and how it can actually recompute that field value. So when it sees cleaner field offset in the netty util internal cleaner Java 6, we know that that should actually be set to the cleaner field of the Java NIO direct byte buffer class. And this takes a bunch of digging. There was fortunately a very helpful blog post that I came across that gave me a lot of pointers in the right direction here. But once we provide that, we can help Graal work around these issues. And then on the other side, for Protobuf, the solution actually turned out to be a bit different. Oops. So for Protobuf, the reason that Graal couldn't pattern match on any of the accesses is that Protobuf's unsafe util class actually has a method for getting the unsafe class if the platform it's on supports it. So in practice, that means all of the accesses on the unsafe class were not directly on the class, they were on the return value of this getUnsafe call. And so Graal says, hey, that's some object being returned from this function. I don't know that that's unsafe. That's the unsafe class, so I can't match any of these things. And there were like, I don't know, 50 to 100 of these errors. And again, this doesn't need to be super high performance. I just want it to work. So the simple solution here was to use the substitute feature to actually replace the definition of this getUnsafe util to always return null. And that was enough that Graal could trace through the code. It could see, oh, I know that the result of this thing is always going to be null. Therefore, all of the conditionals that checked if getUnsafe returned a truthy value now are never going to be true. So I can just elide all of the bits of code that would have potentially been called and made an unsafe access. This turned out to be a lot easier than patching everything else. So where necessary, you can also just kind of plug in your own code into that third-party library. And again, ideally, this is something that would be fixed upstream, but since we don't always have control over the libraries we're using, it is useful to have a surgical knife to like reach in and change just the functionality we need. So now I will actually, let me just go up here. So very similar makefile for Solanum here. I'm going to turn back on the SVM code here, but for explanation, I'm going to disable the reflection config right now, which is the next thing we'll need to fix. Oops. Any questions while this does its stuff?
Yeah, how much of what you know about Java, about the JVM runtime, is applicable to Graal? So like, I'm assuming the substrate VM has a garbage collector. Is it the same C++ code that's in the JVM, and it just like substrated out so that it's actually inside of it? Like, are the object layouts the same? Like, in principle, you could do any of these things differently. I'm assuming it's mostly just reusing the existing JVM code.
It is largely reusing the existing JVM code. The object layouts are not the same, which is why the unsafe utils are problematic. So internally, Graal has to do remapping to its internal object format, which is why sometimes it can pattern match and it knows what the fields will look like on its side, but where it's not, you have to give it help. But I believe much of the garbage collection code is the same, and you do get the full functionality of a heap that you can dynamically allocate into and have it collected for you after the fact, which is one of the reasons that the binaries are large, is that it has to embed all of that stuff that's normally like off in the JVM runtime.
Yeah, I guess the part that's surprising is that like everything in unsafe should be well defined regardless of what like the object layout is. And like in your Clojure Protobuf example, it's literally just that it doesn't know how to look up the GraalVM platform version of unsafe. Right?
Yeah.
Or is there actually some fundamental difference why like the way that like unsafe is an interface, like I know it's not an interface, but except that it describes an interface, doesn't actually work for Graal, or is it just literally just no one's actually glued together a simple thing?
I think it's more the latter. The team that's working on it, I think, has like tried to make it as easy as possible given their resources to map from one to the other. But given that it's not a one-to-one translation, there are just parts that haven't been glued yet. And their stated goal is for this to be a driving or a forcing function for libraries to kind of clean up their act a little bit. How successful that is remains to be seen.
They've been trying to get unsafe out of the scene for 20 years now. So.
Yeah, there's a reason it's widely used.
Maybe one more. What about debugging or JMX or like like what in the JVM world can I actually use to like understand a running program? Or is the answer basically well that's wrong?
That's a good question. I have not delved that deeply into debugging on the native image side. I'd imagine you could do some standard like tracing stuff with like GDB if you really wanted to. So far, it has been more productive for me to work and debug in the Clojure side and then kind of toss it over the fence and see if it works.
And just pray you fit your bug that is only on that VM.
Pretty much, which we actually did run into, and I'll talk about that in a little bit. John knows what I'm talking about. Okay, so not too much longer to build this one, 2 minutes, 50 seconds. You'll note that we didn't get any of those errors this time, which is really nice, although it did yell at us for even referencing the unsafe util, even though this was solely referenced to replace a call that would have returned one of these things. The compiler doesn't know, it's just unhappy with us. Cool, but we got rid of all the errors, so let's try running this thing again. Oh no, it blew up. And this time, oh, we did still get the other events. That's good. Okay, so what happened this time? Well, one of the things that the Riemann output does is it needs to open a connection to the Riemann server in order to send the events. And again, it's built on top of Netty, so under the hood that means opening a Netty channel to that remote Riemann server, and you can sort of see that implicated here. We are calling write events. We are trying to call reconnect on the Riemann client because it hasn't been connected yet. That falls into some Java code here where we open a TCP transport. And then boom, we immediately get an exception here, and we don't even seem to get into the Netty code. I guess you can see that a little bit down here. And so what's going on? This is where we are starting to bump into Graal's no reflection rule. And if you dig a little bit more into what's happening here, by default, when you ask for channels in Netty, you're going to use something called the reflective channel factory. And this is great in Java, like that's most of the time what you want. You just give it a class name and it figures out how to make that from the noarg constructor, except in this case we can't do that. We need to get rid of this reflective access because this class was never loaded at compile time, and as a result it's not present in our generated native image, so the code doesn't have a way to construct it. One way to fix this would be to reach into the Riemann client library and do another substitution and insert our own channel factory that returned a concrete type that would get referenced at compile time, and there wouldn't be any reflection, and we'd be out of this bind. But for reflective cases like this specifically, Graal gives us another tool, which is a set of reflection config. That's very simple. It is basically a JSON file that tells Graal what methods need to be accessible on a given class for reflective invocations. So if at compile time you know a priori what methods you're going to need to talk about, you can do this, and they'll be added to a registry that Graal can use internally so that it knows how to translate those reflective calls to these loaded classes. In this case, it's very simple because we only need one. That is the noarg constructor for NIO socket channel. And we can point this out to Graal and pass it with a little bit of configuration. Oops. This time we don't need to rebuild the Uber jar because none of the code there has changed. So while that runs, I'll talk about the one more restriction that I did run into, which is that if you look in the example config here, there's an HTTP source, and what this does is it makes a simple HTTP request, currently always a GET, to the URL you give it, and then you can write some tests on the response. So you can say status must be in 201 or 429. The data key in the response body, initialized key in the response data should have the value true. The sealed value in the response data should have the value false. If any of these are bad, it sends a event with a failure state. Otherwise, you get a success state. The problem is in the native image, this didn't work when I tried to do it. And it turns out that due to the way the JVM or Java handles URLs and URL protocols, you actually wind up needing to explicitly tell Graal to enable those protocols in the resulting image. And this was pretty surprising to me, especially because I figured HTTP would be a pretty supported one. But especially for things like the SSL engine, apparently Graal will just omit all of that code from the resulting native image unless you say ahead of time that you need it. Unfortunately, this is one area where I've hit a bug I couldn't get around, which is in RC, release candidate 8, which is the tool I'm using to compile this. This doesn't seem to work. So as a workaround, we've had to deploy the Java version of this tool to some of our hosts where we want to use these HTTP checks. But in the future, I hope to get this working so that we can use the native image everywhere. But that is one gotcha that's worth knowing about ahead of time.
Doing some research on that, there were some issues in like 2 or 3 release kit. It's all about JNI related stuff. And I don't know if we're moving in the direction there or not. Might be an avenue to explore in terms of figuring out how to do that.
Yeah, and I've seen at least one blog post that talked about moving some system libraries into the right place so Grail could see them. And that seemed to fix the issue, but more to come.
Java program, right? The GraalVM and stuff, the thing that compiles is a Java program, so it can't see all preemptive libraries.
Yeah, I think so.
Graal project, does it ship a functional JVM?
Yes. Yeah, there's a full Java runtime on Graal's version of the JVM that you can use to also run your code. And I think that is necessary if you want to do some of the polyglot support, because the runtime is what has the substrate VM embedded in it for running the other languages that have been compiled down to SVM bytecode. Okay, so that's done compiling, and if the demo gods are favorable, hey, well, you can't see the Riemann side, but it successfully reported the events to both the terminal and sent them off to our Riemann server. So we now have a functioning binary, and just to do that. Cool, so 1.34 seconds of real time. And this is largely due to needing to go collect all this information, some of which involves shelling out. So not quite as fast as our nice self-contained Eden Pretty printer, but still plenty fast and performant for a program we want to run in the background.
What is the difference in the network with JVM?
Sure. Okay, so 36 megs of RAM, 1.34 seconds in the native version. .3 seconds in the UberJar version, and we are back to 268 megs of RAM. So again, something we want to run in the background in all of our boxes. Having 32 megs of RAM used is a lot nicer than 268.
What's the runtime performance like? So like if I compare something that's like, let's say with CPU heavy, is it actually about the same as like what the JRE is, or?
In terms of like throughput and
Yeah, like let's say you're throughput bound and you're just like turning, forget IO for the moment, you're just CPU bound.
I suspect they would be similar, although I haven't done extensive testing of that. I think the shorter your total runtime is, the more the native image would win, just because of the startup overhead. But the hotspot compiler is like really good, so I'd expect that over long enough runtime, the JVM version would be better or pull ahead. Cool, that's the end of my content. So if you guys have more questions, I'm happy to answer them. Otherwise, thanks for coming to Seajure.